Welcome back, everyone. Ready for another deep dive?
Always.
Awesome. Today, we're going to be going, well, pretty small.
Smaller than small.
That's right, quantum hardware.
The future of computing.
Exactly. We'll be focusing on, let me see.
Jorgo Schneepot?
Yes. His essay, Quantum Hardware, Basis für die Technologie der Zukunft,
A fantastic piece.
really lays out why this stuff is so revolutionary. I mean, we were talking about computers that can,
Well, they use quantum mechanics
yeah,
to process information in a totally different way.
completely different, not just faster, I mean,
Right, completely
a
different.
whole different ballgame. We're talking about simulating molecules.
For drug discovery,
Yeah.
breaking encryption that's impossible to break today.
Stuff that would take normal computers, I don't know,
Millions of years.
millions, yeah. So, how about we start with the basics?
Sure.
For anyone who maybe needs a little refresher.
Okay, so the heart of it all is this idea of a qubit.
Okay, equivalent.
Yeah, instead of a bit like in our normal computers, which can be a 0 or a 1, a qubit can be,
Both at the same time.
yeah, superposition, they call it.
Superposition, yeah.
It's like,
Like a spinning coin?
yeah, a spinning coin, you don't know if it's heads or tails until it stops.
Exactly, so it's both at the same time.
Exactly.
Wild.
And then you've got entanglement. Schnittpack, he really emphasizes this.
Yeah?
It's where two qubits, they get linked together.
Linked.
Yeah, no matter how far apart they are. It's like, imagine you have two of those spinning coins,
Right.
but they're miles apart.
Okay.
And when one lands on heads, the other one.
Lands on heads, too.
Every time.
So they're connected somehow.
Yeah, it's spooky action at a distance, as Einstein called it.
Spooky. So Schneepat's saying that this entanglement, it's really what makes quantum hardware.
Totally different, yeah.
Different, yeah. Not just a faster computer, but
A whole new way of thinking about computing.
okay, so we've got our qubits, we've got entanglement, but how do you actually build these things?
Right, well, there are actually a bunch of different ways.
Oh, right.
Schneepat talks about a few of them.
Like what?
Well, you've got superconducting qubits,
Okay,
which are probably the most advanced right now.
the most advanced.
Yeah. Google and IBM, they're using those.
But they have to be kept really cold?
Yeah, super cold, which is a challenge.
Gotcha. What else?
There are ion traps.
Ion traps, okay.
They're very precise, but it's hard to scale them up to a lot of qubits.
Okay, I see. Schneepat mentioned some other stuff too, right?
Yeah, he talks about photonic systems.
Photonic, okay.
They use light particles,
Light particles, wow.
which is good for communication.
Right,
Not so much for, like, heavy-duty computation.
makes sense. And then there's that really out there stuff.
Oh, yeah, topological quantum computers.
Topological.
They're still very theoretical,
Right, early stages.
but they could be really good at error correction. Schneepet thinks they have a lot of potential.
Interesting, so a lot of different approaches.
Yeah, a lot of different options.
And it sounds like they're even combining them, right?
Yeah, hybrid systems.
Hybrid systems.
Taking the best parts of each approach.
Wow. So it's still early days,
It is, yeah.
but it seems like a lot is happening.
Oh, absolutely. Lots of exciting breakthroughs happening all the time.
Like, what was it, quantum supremacy?
Right. Google,
They did it.
they built a quantum computer that could do something
Something, yeah.
that no classical computer could do.
In a reasonable time frame.
Yeah, Schneepat mentions that in the essay. It was a major milestone.
Show that this stuff, it's not just theory anymore.
Definitely not.
It's real. And not just Google, right?
Right. Lots of companies are making progress.
And the number of qubits they can,
It's increasing all the time.
it's increasing, yeah. And Schneepat also mentioned some cool stuff with quantum communication, right?
Oh, yeah, like China's MISHIS satellite.
Mischievous.
It uses quantum entanglement
To communicate securely.
over huge distances.
Like unbreakable encryption.
Potentially, yeah.
Pretty amazing. It sounds like there's a lot of potential here.
Oh, absolutely. But there are also some big challenges,
Challenges.
right, that we need to overcome.
Yeah, let's dive into those next.
Sounds good.
So, challenges. What are we talking about here? What does Schneepat say?
Well, one of the biggest is decoherence.
Decoherence.
Yeah, the quantum states, they're very fragile.
Oh, right.
And it's easy for them to get, I don't know.
Disrupted.
Yeah, disrupted by noise, heat, all sorts of environmental factors.
So they lose their quantumness.
Exactly. It's like Schneepat uses this analogy.
Oh, yeah.
It's like trying to build a house of cards in a hurricane.
Okay. Yeah, that's a good one.
Everything's just constantly trying to knock it down.
So how do you even deal with that?
Well, error correction is a big area of research,
Error correction, okay.
but it's way more complicated than with classical computers.
Because you're dealing with these
Qubits that can be in multiple states at once.
right, right. It's not just a matter of flipping a bit back to the right value.
Exactly.
Okay, so that's decoherence and error correction. Schnepp mentioned some other challenges too, right?
Yeah, scalability is a big one.
Scalability, yeah.
Building a quantum computer with a few qubits, it's one thing.
Yeah.
But getting to millions of qubits, that's a whole other challenge.
And you need millions, right? To
to,
do
to do those really complex calculations that we've been talking about.
yeah, the really interesting stuff.
Exactly. And then there's energy consumption.
Energy.
Some of these systems, like the superconducting ones,
Yeah,
they need to be kept incredibly cold.
which takes a lot of energy.
A lot of energy, yeah. So we've got a ways to go.
Okay, so challenges, challenges. But even with all that, there's still
Tons of potential, yeah.
so let's dive into that. What are the applications here? What does Schnepp see as the big ones?
Well, one area that Schnepphead is really excited about is materials science.
Material science. Okay.
Imagine being able to design new materials at the atomic level
Wow.
using quantum simulations.
So instead of like mixing stuff in a lab and seeing what happens
Exactly. You could design a material with the exact properties you need.
from the ground up.
From the ground up, yeah.
That's incredible. What kind of materials were we talking about?
Well, Schnepphat gives this example of the FOMOCO molecule.
FOMOCO,
It's a complex molecule that's involved in nitrogen fixation,
nitrogen fixation.
which is how plants take nitrogen from the air and turn it into something they can use.
So like fertilizer?
Exactly. If you could simulate that process accurately.
We could maybe make fertilizer production more efficient.
More efficient, less energy intensive, yeah.
Wow. So that's one application. Schnepp talks about drug discovery too, right?
Oh, yeah, that's a big one.
How would that work?
Well, you could use quantum computers to simulate how different molecules interact with the body.
So you could design drugs that are more effective.
More effective, fewer side effects.
Right.
And you could do it much faster than we can today.
So we're talking about like potentially curing diseases that are currently incurable.
Potentially, yeah.
That's pretty amazing.
Huh.
But Schnepp also mentions some potential downsides, right?
He does, yeah. Particularly in the area of cryptography.
Cryptography, right?
Quantum computers, they could break a lot of the encryption that we use today.
Really?
Yeah, like Shor's algorithm.
Shor's algorithm, yeah.
It can factor large numbers much faster than a classical computer.
Which is what a lot of our encryption is based on.
Exactly. So we need to start thinking about quantum-resistant encryption.
Like now.
Yeah, pretty much. Schnepphat is pretty clear about that.
So that's a bit of a double-edged sword.
It is, yeah.
On the one hand, you've got unbreakable encryption, but on the other hand,
You've got the potential to break all the existing encryption.
right, right. Okay, so we've got materials, science, drug discovery, cryptography. Schnepp mentions anything else?
Yeah, he talks about optimization process.
Optimization. Okay.
Things like logistics.
Logistics.
Finding the most efficient way to deliver packages.
Or like traffic flow.
Yeah, or even things like financial modeling.
So anything where you're trying to find the best solution out of a lot of possibilities?
Exactly. Quantum computers could be really good at that.
Okay, so that's a pretty wide range of applications. And it sounds like Schnepp is really thinking about
The bigger picture, yeah.
the bigger picture, yeah. Not just the technology itself, but
How it's going to impact society.
impact society, right? Let's talk about that next.
Okay.
So, where do we go from here? What's next for quantum hardware?
Well, Schnepphat lays out some pretty clear trends in his essay.
Okay, like what?
One of the big ones is, well, better qubits.
Better qubits.
Yeah, I mean, we're already seeing a lot of progress there.
Right, like with
Coherence times
coherence times, yeah.
getting longer, meaning those qubits can stay in those quantum states for longer.
So, less susceptible to decoherence.
Exactly.
More stable computations.
More stable, more complex, yeah. Schnepphat also talks about scalability.
Right, getting to those millions of qubits.
Right. He sees a lot of potential in modular systems,
Well, actually,
like building bigger quantum computers out of smaller units,
kind of like
like Legos.
yeah, like Legos. That's a good analogy.
Yeah.
And then there's this whole idea of
Hybrid systems.
yeah, hybrid system.
Combining quantum and classical computing. Schnepphat, he's a big believer in that.
Makes sense. I mean, classical computers, they're still really good at
A lot of
A
things.
lot of things, yeah. So it's not about replacing them.
It's about using the right tool for the right job.
And the right tools are
Fitting together.
working together, yeah.
Yeah.
And Schneppat also talks about this,
Cloud-based quantum computing.
yeah, cloud-based. So basically,
Accessing quantum computers over the internet.
like we do with,
Data storage,
data storage, yeah,
software, all that stuff.
makes it more accessible.
Way more accessible. Schneppat thinks that's going to be a big driver of adoption.
So better qubits, bigger systems, easier access. Sounds like a recipe for
A quantum revolution.
quantum revolution, yeah.
Yeah.
But it's not just about the technology,
All
right?
right. Schneppat, he spends a good chunk of the essay talking about
Societal impact.
the societal impact. Yeah. The economic shifts, the new jobs that'll be created, the ethical questions.
Like, with AI and all that.
Exactly. It's something we need to be thinking about now.
So we've got a lot of work to do,
We do. Yeah.
but also a lot of potential.
Tons of potential. I mean, think about it. If we can harness this quantum weirdness
Quantum weirdness, yeah.
to solve problems that we can't even imagine solving today, who knows what the future holds?
Yeah, it's pretty mind-blowing. Well, I think that about wraps up our deep dive into quantum hardware.
A fascinating topic.
Big thanks to Jorgo Schneppat for his insights. His essay really got us thinking.
It did, yeah.
And to all of you after listening, keep exploring, stay curious, and who knows, maybe you'll be the one to make the next big breakthrough in quantum technology.
Until next time.
See ya!